Good afternoon. I always seem to start this way by trying to say it's nice to see you. Of course, I can't see you. It's nice to see you, that you're there, and I hope you're all well. We'll start as usual now. So today's lesson is called Transformers. And as I usually do, I'll give you 3 minutes. And could you do the usual jobs? I'm assuming many of you are still keeping up with all the details in your book. So put the title in your book, update the contents, look back over stuff we've done last time, because I'll be doing a quiz in 3 minutes time. So I'll put 3 minutes on the clock. That's 12 minutes, let's try again. 3 minutes on the clock. Usual jobs, please. I'll be checking the comments if there's anything people are wanting to ask me about last time. But 3 minutes to do those jobs, and then we're going to start with a quiz. So the last thing I'll say for now is, if you like to do that quiz on scrap paper, then just make sure you've got a piece of scrap paper ready. Thank you. Three minutes there, hopefully enough time to do those usual jobs. And without further ado, I'll start the quiz as has become sort of the tradition of these lessons. I'll do 5 questions on things that are from longer ago, and then 5 questions of more recent stuff. And we'll stop after the first 5 to go through them, then do the second 5. So if you've got a bit of scrap paper to hand, that would be ideal. Question 1. What does the milli, or lowercase m, prefix stand for? What does milli, in terms of a unit prefix, what does it mean? What does the milli prefix mean? Question 2, something to draw. Could you draw the IV characteristic for a filament lamp? Question 2, please draw the IV characteristic for a filament lamp. Question 3, What is the resultant force on an object that is at terminal velocity? What is the resultant force on an object that is at terminal velocity? Question 4. What happens when two objects of the same charge are brought together? What happens when two objects of the same charge are brought together? And then question 5. How are ammeters connected in a circuit? Sounds general that, but it has a specific response. How are ammeters connected in a circuit? We'll go through each of those now. So I hope that wasn't too quick. I was trying to make them snappy and not drag too much. We'll go through each one in turn. Starting with what the milli prefix means. That was question 1. Well, there's a few ways you could express this, but in terms of standard form, it means times 10 to the minus 3. You could say that means it's divided by 1,000, or you could have put something more wordy, in other words, something like it's 1,000 times smaller than the original unit. The best answer there, probably times 10 to the minus 3. It's shorthand for that, but any of those would do. That's what milli means. Next, the IV characteristic for a filament lamp. I feel like we've had that question sometime recently. IV characteristics start with a diagram like that, with potential difference there, V, and current there, I. And for a filament lamp, you tend to get this shape. A slight curve, not going flat, you'll notice, tending towards a limit, not reaching a limit, not going flat. And the idea with this is that it's showing that the component's resistance increases. In other words, as a filament lamp gets hotter, its resistance increases, and that's shown from the shape of this graph. That was question 2. Question 3, what is the resultant force on an object that is at terminal velocity? 0. 0 newtons was the answer there. Question 4, what happens when two objects of the same charge are brought together? So either a positive and a positive, or a negative and a negative. Well, those two objects would repel each other, and that's what I was looking for there. They would repel. And then question 5, how are ammeters connected in a circuit? Well, the answer is they're connected in series with the component that's being measured. They're connected in series with the main loop of the circuit. The key word there in the answer is in series. That's the key phrase. So ammeters connected in series. Right, now 5 questions on things that are more recent. Some of these you'll be very familiar with, some less so. Where is the magnetic field strongest in an electromagnet created by a coil of wire? Or, put another way, where is the magnetic field in a solenoid the strongest? Where is the strongest field in a solenoid? Question 1 of this second bit. Question 2. Sounds again like it's a vague question, but it has a specific answer. An induced current has a magnetic field. In what direction will this field act? An induced current has a magnetic field. In what direction will this field act? That was question 2. I hope that's long enough for that one. Question 3 is another graph sketch to do. Could you sketch the potential difference time graph produced by an alternator? Could you sketch the potential difference against time graph produced by an alternator? Just give an extra moment on that. I feel I was going a little bit fast. Question 4. I rather feel I gave this away a couple of questions ago, but give the name for a coil of wire. Give the name for a coil of wire. That's question 4. And then question 5, what is the name for when a current is induced in a conductor that is moving in a magnetic field? I'll say that phrase 2 more times. Once you understand it, I think the answer is quite easy for most of you. But I'll say it again. What is the name for when a current is induced in a conductor that is moving in a magnetic field? What is the name for when a current is induced in a conductor that is moving in a magnetic field? Right, and to go through those 5, the first of those 5 was, where is the strongest field in a solenoid in a coil of wire? And it's strongest within the coil. The answer was within the coil. Question 2, an induced current has a magnetic field. In what direction will this field act? Well, we wrote this phrase down a few lessons back now. That field will act in a direction to oppose the change that created it. So the answer to the question, in what direction will this field act, is in a direction to oppose the change that created it. I think that was a tricky question. Question 3, sketch the potential difference time graph produced by an alternator. Well, something like this. You need a graph that has axes in the positive and the negative direction for an alternator. And this is positive voltage here, negative voltage there, 0 there. You don't need all of those on, just that would do, but they're the labels I would add on something like this. And an alternator does produce alternating current. So not only does it go in the positive direction, but also in the negative. Something like that, as many wave cycles as you want. But that is a graph of the potential difference produced by an alternator. Question 4 is the one I somewhat gave away. Gives the name for a coil of wire. Answer, solenoid. And then question 4, what is the name for when a current is induced in a conductor that is moving in a magnetic field? What I was describing there was the generator effect. I'd accept the answer electromagnetic induction as well, but the answer I've got here, the generator effect. So, as you wish, you can keep account of that. I guess that was out of 10 or out of 2 lots of 5, you can keep account of that. But we will start, and we're going to learn about transformers today. And at the end of the last video, or live stream, whatever you want to call it, I said my task for the week was to build a transformer with materials that I had. Well, I have managed. What I'm going to do is I'm going to show you what I've built by diagram first, because when I show it, it will just look like a mess of wires on the table. So I'm going to show you what I've drawn, and in so doing, try and explain what transformers are. Once we've done that, and once I've shown you my building of a transformer, we'll make some notes together, and then, as always, there'll be some questions to answer to end the lesson. I'll try and keep it snappy, I'll try and keep it to the point, but I'll try and make it as clear as possible. Just checking, no, I've had no questions so far. So I'm going to sidle up to the camera again with this, and I'm going to draw a circuit that shows the transformer I've built. And perhaps the first thing I need to say actually is that you'll see that a transformer isn't just one circuit. The point of a transformer is that it links 2 circuits, not electrically, but magnetically. It goes something like this. So the transformer I've built is built around basically what I could find, which was an iron nail. So an iron nail is at the heart of this, a piece of iron. Iron is a metal that is easily magnetized. It's a really good, and we've learned about these, it's a really good induced magnet. Really good material to make an induced magnet from. And what I'm going to have is 2 circuits. Circuit number 1 will wrap around the coil. Yeah, sorry, we'll wrap around the nail in a coil like that. And I'm going to be putting, I think, 4 volts into this. I can't go too high on the power pack because of heating. Again, this is not really a complete circuit in the sense we understand it. It's what's known as a short circuit in a way, because there's no components, it's just wire. So this will heat up quite a lot. But then also wrapped around it is a second circuit. And I'll show that here. So there'll be a second circuit, second coil wrapped around this. And onto that, I'm simply going to attach a voltmeter, like that. So this is simply, this second one, a coil of wire. There's no power source in this. That's an important thing to note. There is no power source here. It's not producing its own power, its own flow of current. But we now know the generator effect. So what's going to happen is that because these are not, they're not electrically touching, this is going to be an insulated wire, so there's no current flowing from here into this one, but they are magnetically linked. So if I make a current flow in this one, it will create a magnetic field, and this one will experience that magnetic field. But there is one last thing to make clear. This is slightly misleading, what I've drawn here, because a battery makes DC, direct current, one flow of current around this. Now that wouldn't work for a transformer, because for the generator effect to work, you need a changing magnetic field. And we only get a changing magnetic field by using AC, not DC. So instead of having that symbol, I'm going to change it for this symbol. And so what I want you to imagine coming from the power pack is 4 volts still, but of AC, alternating current, going one direction, then the other. So how transformers work is something like this. You create an alternating current in a first coil, sometimes known as the primary coil. You create an alternating current in that first coil, and that makes a switching magnetic field, an alternating magnetic field here, which permeates through the iron. Well, because we've then wrapped this second coil around it, we can call it a secondary coil. Because we've wrapped a secondary coil around it, this secondary coil will feel that alternating magnetic field, and through the generator effect, it will induce an electric current in this second coil. And we'll be able to measure the voltage being produced there by putting a voltmeter in there. So that's how I've made my transformer, and that's the beginnings of how it works. You create an alternating current in one coil, and then you magnetically link it to a second coil. And that second coil, because it's magnetically in contact, not electrically, but magnetically in contact with that first coil, it will experience a changing magnetic field. And through the generator effect, we know that means it will experience a changing potential difference, which we'll measure there. Now I'll show you the one I've built, and hopefully that will now make some sense to you. Pausing again, I can't see any questions coming in yet. I wouldn't expect any yet. Just checking. And there's no good place for me to show this, but let me just show you each bit one by one. So here is the beginnings of it. This is the primary circuit. And so when I switch this on, it's going to be 4 volts. It's pointing to 4 there. And I've switched it not from DC, that would be DC, but I've switched it to AC. So this is producing 4 volts of alternating current. And it's being fed into the black wires here. So all that's happening is there's a wire coming in there. It's wrapping around that about 10 times, and then the wire coming out there. And it's connected up with a crocodile clip somewhere off screen. And then on the same piece of iron, I have my secondary coil. I've deliberately chosen a different color of wire to make it clear to you that these are not electrically joined together. These are 2 separate circuits. And so on the same piece of iron, there is a secondary coil. And that secondary coil is going to a voltmeter. Now it looks like quite a complicated voltmeter, and that's because it's actually an oscilloscope. But here's my reminder to you that oscilloscopes are basically just voltmeters. And it's actually the oscilloscope I'm going to show you now. So I'm just going to angle things so that hopefully you can see that well enough to see what's going on. This is an oscilloscope. This is an oscilloscope screen. When I switch it on, And when I turn the whole circuit on, you will see what sort of voltage is being produced. So I'll turn this on first. And in a moment, it always takes a minute. It's like an old-fashioned television. You'll just see a line going across there. The reason it's flashing is just because of the sample rate I've got here. Each square at the moment is representing 10 milliseconds. Turned out to be the best setting for me to show you what I wanted to show you. So take in what you're seeing there, and now look at the difference when I turn on the first circuit. Remember, this is measuring the secondary circuit, and at the moment there's nothing in the secondary circuit. Well, I'm about to turn on the primary circuit, and you'll see that it induces a voltage in this secondary circuit. At least I hope so. Well, there we have it. So I hope this is proof enough that we are inducing a second voltage in that secondary coil. We are getting an alternating voltage because we had an alternating voltage in the first coil. So there's an alternating voltage in the first coil. That created that alternating magnetic field, which through the generator effect made an alternating voltage, an alternating potential difference in the secondary coil. We transferred the electrical energy from one circuit into the other. And that's what a transformer does. It transfers electrical energy from one circuit through the generator effect into a second circuit. And you might have just seen that go off now, and it coincided with a click. Well, actually, that was the power pack tripping out because of those heating effects I talked about before. This doesn't work for long. So I'm going to switch it on, reset it, and just do it one more time. It's a safety feature of the power packs. When they sense that a circuit is a short circuit, they just trip out before it gets too hot. But I'll turn it on again, and again you will see that we are inducing a potential difference. And there we have it. So I was successfully able to build a transformer with what I had. Well, what we're going to do now is make some notes about all of that. That's, I think, the most sensible thing to do now. I hope that was clear enough. Because wires get very messy, I wanted to show you the better picture of it first. That's essentially what I had. My primary circuit and my secondary circuit linked in a sense by this piece of iron, but not linked electrically, linked magnetically, which means whatever happens here ends up being reflected over here. Well, before we make those notes, I also want to show you a better diagram of a transformer now and how they're actually made on the board. And then we're going to start making some notes together. So let me just zoom into that for a minute and just bear with me while I do so. Right, I think that's pretty clear to see on the screen. So this is more how transformers are laid out. The one I did, remember, that was side by side, but actually that doesn't tend to be how they're laid out. They're laid out around a central sort of loop of iron. This is known as a core, and it's normally a good solid piece of iron in the middle. And then you have primary coil here, secondary coil there. Well, look what's happening. In the primary coil, we've got an alternating current. Look at the arrows going one way and then the other. We have an alternating current. Well, as that alternates, it creates an alternating magnetic field in the core. And I hope you can see just about, they rush at quite a speed. But first, there's a magnetic field flowing one way, then the other way. If I just pause for a moment, you'll be able to hopefully see that on your screens. So you've got an alternating current producing an alternating magnetic field. And then we move around to the secondary coil. Because this secondary coil experiences this alternating magnetic field, through the generator effect, it produces an alternating current in that secondary coil. And that's how transformers work. They are two separate circuits linked magnetically so that a change in this first circuit produces the same change in that second circuit. Last thing to say before we make notes is this transformer, in a sense, wouldn't be very useful because count the coils. 1, 2, 3, 4, 5 coils there, and 1, 2, 3, 4, 5 coils there. So let's say I had, I don't know, 500 volts in this first coil. I would have 500 volts in the second coil. Transformers get really useful when you alter the number of coils. So let's say now I had 5 here, but I had 500 here. Then I might have a certain amount of voltage here, but I would have substantially more over here. I'd have stepped up the voltage. Or you can do the reverse. If you have more coils here than you have here, then you actually decrease the voltage going from one to another. And that's really why they're called transformers. They allow you to transform how much potential difference there was in the first circuit compared to the second. They allow you to either step up or to step down the potential difference. Time for some notes, I feel. So you'll need pen, pencil, and ruler. I'll be adjusting the camera. Just get yourselves ready to take these notes. Right, and we'll start with a sort of defining sentence. Diagrams are going to do a lot of the work for us here, as they often do. They're often the most useful way to take notes. But I think we'll start with this, what transformers actually do. We don't need a subheading because the title was Transformers. And we'll start by saying this. So I'm just going to take my timer off so it doesn't make any noise. We'll start by saying this. Transformers transfer electrical energy Transformers transfer electrical energy from one circuit and in brackets I'm going to give it a name, primary. So transformers transfer electrical energy from one circuit, primary, to another, secondary, in brackets. Right, now I'm going to try and draw something like the transformer you just saw on the screen. As you'll appreciate, I'm going to keep the diagram as simple as possible, not only because I'm working felt tip, but then I think it also works well for you too. Well, we start on transformers with the core. So the first thing to draw, and you can try and scale it roughly to the same size I'm doing, and I'm not going to use a ruler for this. I don't think we need to, but you may wish to if you want to give it a slightly neater feel. But we have a core of iron. And the core of iron we'll draw in this rectangular shape, space to the left and to the right. And sure, it's not just one big block, we'll do that. And we'll label it underneath as iron core. And the reason we go for an iron core, I think I'll also write in this little label. We choose an iron core because iron is easily magnetized. If you think about that for a minute, it makes sense. Certainly the transformers we use in the national grid, well, our electricity has a frequency of 50 hertz. In other words, it changes direction 50 times a second. So you need a material that can magnetize and demagnetize and remagnetize in the opposite direction really very quickly. And that's why iron tends to be chosen for this job. It's very good at doing that. So transformers built around this iron core, and you have a primary coil. So we'll bring in and just show it, imagining that it's wrapping around the back like that. So 1, 2, 3, 4, and I'm going to go for 5 loops, like on the diagram that we saw. And then a secondary coil here. So again, 1, 2, 3, 4, 5 loops. I did say to you that's a slightly useless circuit in that sense, a slightly useless transformer, because it's not stepping up or stepping down the voltage. But for understanding how the transformer works, I'm just going to keep it simple in that sense. So we'll give this side a name. We'll give this side a name, the primary coil, and this side the secondary coil. I think very little to add, but I do want to make it clear from this diagram that it needs alternating current to work. So we'll show that on this primary side, there is a source of AC. So the symbol looks something like that. There's 2 circles and a squiggle in between. But to make it abundantly clear, we'll write AC. And so that's really showing that's the source that has the power input. But that, yes, that electrical energy through this magnetic link is being transferred into this one. And so a bit like we had before, we'll just show a voltmeter or something here, measuring what's coming out. And that's a transformer. It transfers the electrical energy from one to the other. Well, underneath that, I want 2 simple diagrams to show how a step-up transformer would work and a step-down. So I'm going to put those side by side. Bit risky, but especially working in felt tip, but I think there'll be room. So underneath, draw 2 transformer coils, deliberately smaller than the other 2, because we're going to have to fit room around these things around these 2. So there's my 2 cores. They're meant to be identical, which I think they more or less are. And on this first one, we're going to do an example of a step-up transformer. So we've not got a huge amount of room to work in. So let's really exaggerate it. This first one's just going to have 2 turns of wire around it, like that. 2 turns of wire. But coming out, it's going to have, well, let's fit as many as we can, maybe 8. 1, 2, 3, 4, 5, 6, 7. 7 is all I can fit. Just fit as many as you can there, like that. And to keep things shortened in shorthand, I'm just going to put voltage from the primary, VP, and you're going to get used to this. Next lesson, we're going to learn some equations that use this, and voltage in the secondary here. Well, if you had that sort of layout where you have primary 2 coils and many more coils on the secondary, this would be a step-up transformer. So we'll just write step up. And then we'll draw what a step-down transformer would look like as well. So in the step-down case, lots of turns on this first one. Again, I'll fit 6 or 7 in, I think, comfortably. And this one, again, voltage in the primary. And then on this one, a reduced number of coils, in this case, just 2. And that's showing the voltage coming out in the secondary. And that's what a step-down transformer would look like. Last thing on the notes we're going to do, and I'll need a separate page for it, is we're just going to put into words a more sort of complete description of how a transformer works. One of those bullet point descriptions like we use for the microphone, like we use for the loudspeaker, just so that you have it for reference when you're attempting some questions. So that's how transformers are built. This coming up now is how they work. So perhaps a subheading. And could we put the subheading, how transformers work? Let me just underline that. And it starts, and we're going to do these somewhat in note form. So rather than using the phrase alternating current, I'm going to use AC and trust that you now understand that. You've been exposed to that shortening for long enough. So it starts here. AC flows in primary coil. Well, remember, whenever a current flows, you have a magnetic field. And because it's an alternating current, it's going to be an alternating magnetic field. I'm not going to use the word alternating, I'm going to use the word changing. So this creates a changing magnetic field in core. And again, that's note form, but in the core or in core. Now we just need to describe what effect that will have on the secondary coil. So we can say, we're going to bring in the word induces here. Changing magnetic field induces alternating current in secondary coil. Perhaps unnecessary, but in brackets I'm going to put generator effect. It's just an example of the generator effect. And then I'm just going to add a general note about how changing the number of coils affects it. So number of coils on primary / secondary determines the type of transformer. And in brackets, I'm just going to put step up / step down. And I think that's all I need to say as to how transformers work. Well, I'm about to set you off on some work of your own. Just want to show you one last thing on the screen. Just pausing just in case anyone's keeping up with me, but I guess you can always look back after this lesson if you got lost in any of those notes. So I'm just bringing this back to the screen just to show you one last thing, and I don't think I need to zoom in for it. Just want to show you the national grid again, because I want to cast your mind back to about a year and a half ago. I taught you about the national grid, and we just had these mysterious boxes here and here. On this diagram, they're labelled C and D, and we said they were transformers, and we said this one was a step up and that one was a step down. And I just like bringing you back to this moment, because now you know exactly what goes on in those mysterious buildings called transformers. This one's a step up transformer, so there'll be fewer coils going in than coming out. And so the voltage increases, goes from about 1,000 or so volts there to a few 100,000 volts up here. Well, that's too much for the home, so then there's a step down transformer at the other end of the line. There'll be more coils going into that, coming from the power lines, more coils going in than are coming out. And so that means the few 100,000 volts steps down to 230 volts for the household. But that's the transformers we talked about all along. That is how they work. They have an iron core and they have two very separate coils. And so you re-look at this national grid picture and you realize it's three separate circuits. The circuit in the power station, leading some coils. The circuit in the power lines, leading some coils at this end. And then the circuit in the household, a third circuit. So it's not just one big circuit, it's three circuits that are magnetically joined together by the way transformers work. Right, time for you to do some work, I feel. So what I'd like you to do, I've sent ahead the questions, haven't I? And I think you'll like them, in that the first one is a description of transformers and how they work. But the second one brings in some stuff from last year about electricity. When I say I think you'll like them, I really mean I think you'll find them challenging, and that's got to be a good thing. I think I'll try and give a fair amount of time. Now there's 18 marks worth here. I'll put 15 minutes on the clock and we'll go through it, and that's the lesson. And I hope that 15 minutes is going to be enough. So off you go, good luck, and just ask me for help if you need help with any of it. "15 minutes, good luck." You've had a little over half of your time. Towards the end, I'll ask if you need more time. And just while I'm interrupting the silence, I'll just say one thing, which is the very, very last question. That's 2C part II. Does involve an equation I've not taught you yet. Nevertheless, I think some of you might be able to give it a go. But 2C part II does involve an equation I haven't taught you yet, sort of. Actually, you can do it using equations I've already taught you. And it'll be interesting to see if any of you do manage. Anyway, you've got 6 more minutes. Sorry, Max, yeah. Just so you're coming as I finish saying that. Yeah, there is an equation that I haven't taught you, but there is one in your head that actually does the job anyway. somewhere under 2 minutes now. It tends to be at this point I give warning. If anyone wants a little longer, just say so now and I will give you longer. But assuming not, we'll be going through this in 1.5 minutes.